Imagine discovering that one of the most famous ideas in science fiction is not just unrealistic, but physically impossible in ways far more terrifying than most people realize. For decades, movies, books, and futuristic concepts have convinced us that space travel at near light speed is mainly an engineering problem. Build a powerful enough engine, create stronger materials, and eventually humanity will cruise effortlessly between planets while stars stretch beautifully across the windows of our ships. It sounds elegant. It sounds inspiring. But according to the deepest laws of physics ever discovered, that vision collapses the moment real mathematics enters the picture. The central misunderstanding begins with a simple assumption that almost everyone carries without questioning it. We imagine space as empty, a silent vacuum with nothing inside it. And if there is nothing there, then moving through it faster and faster should create no resistance, no danger, and no meaningful consequences beyond acceleration itself. But this idea is fundamentally wrong. Space is not empty. In fact, space is filled with invisible energy left behind from the birth of the universe itself, and at extreme speed, that invisible background transforms into something unimaginably destructive. To understand why, picture yourself standing outside during a gentle rainstorm. The rain feels harmless. Tiny droplets tap against your skin softly enough that you barely notice them. There is no danger at all. Now imagine stepping into an experimental aircraft capable of traveling 3,000 miles per hour and flying directly through that exact same rainstorm. The water has not changed. The droplets are still small. Their chemical structure is identical. Yet your relationship with them has transformed completely because of your speed. At that velocity, each droplet strikes with explosive force. The windshield shatters instantly. Metal tears apart. The vehicle cannot survive. The storm never became hostile. Your speed weaponized it. That same principle applies to relativistic space travel, except the consequences become vastly more extreme because the rain in space is not water, it is radiation. Modern cosmology tells us that the entire universe is submerged in something called the cosmic microwave background. This is ancient electromagnetic radiation left over from the earliest moments after the Big Bang nearly 14 billion years ago. When the universe was born, everything was unimaginably hot and dense. As space expanded over billions of years, that ancient light stretched and cooled until it became weak microwave radiation barely above absolute zero. Normally, this radiation is harmless. Every second, countless microwave photons pass through your body and through Earth without causing damage because their energy is incredibly low. We exist inside this ancient sea of light constantly and never notice it. But relativity changes the situation completely once velocity increases. As a spacecraft accelerates through the cosmic microwave background, the photons in front of the ship begin undergoing relativistic blueshift. Their wavelengths compress, their frequencies rise, and as frequency rises, energy rises with it. At first, the effect seems manageable. The microwave radiation shifts into infrared wavelengths, producing heat. Accelerate further, and that same radiation enters the visible spectrum. Suddenly, the darkness ahead of the spacecraft begins glowing with concentrated light. Push deeper into relativistic speeds, and the transformation becomes catastrophic. Visible light compresses into ultraviolet radiation, then X-rays, then hard X-rays, and eventually gamma rays. At that point, the harmless ancient radiation filling the universe has become a concentrated wall of lethal high-energy gamma radiation directly in front of the spacecraft. And none of it came from a nearby star or black hole. The ship created the danger itself through its own velocity. Gamma radiation does not simply warm surfaces. It penetrates matter at the atomic level. It strips electrons from atoms, destroys molecular bonds, damages electronics, and tears through biological tissue with devastating efficiency. Any crew inside such a vessel would receive fatal radiation exposure almost immediately. The ship's internal systems would fail. Structural materials would begin degrading atom by atom under continuous radiation bombardment. The terrifying part is that nothing in the environment changed. Space remained exactly what it always was. The danger emerged entirely because motion altered the physical interaction between the ship and the universe around it. But this is only the first layer of the problem. According to quantum field theory, the vacuum of space is not truly empty at all. Beneath apparent emptiness exists a fluctuating quantum structure where virtual particles constantly appear and disappear faster than direct observation can normally detect. Empty space is actually a restless quantum field simmering beneath reality itself. This leads to one of the strangest predictions in modern physics, the Unruh effect. The mathematics predicts that an accelerating observer does not experience the vacuum the same way as a stationary observer. To someone standing still, empty space appears cold and dark. But to someone accelerating with enormous force, the vacuum begins to appear warm. The faster the acceleration, the hotter the vacuum becomes. In other words, acceleration itself can make empty space radiate heat. At ordinary speeds, the effect is tiny and undetectable. But the extreme accelerations required to push a spacecraft toward relativistic velocity would raise this vacuum temperature dramatically. The spacecraft would no longer only face gamma radiation ahead. It would also be immersed in thermal radiation generated by its own acceleration through the quantum vacuum. The ship would effectively begin cooking inside apparently empty space. Now combine these two realities together. A vessel accelerating toward near light speed would face a concentrated wall of blue-shifted gamma radiation in front, while simultaneously being heated by the quantum vacuum itself. And beyond all of this stands the final barrier, Einstein's special relativity. According to relativity, the closer a massive object gets to the speed of light, the more energy is required to continue accelerating it. This increase never stops. To actually reach light speed would require infinite energy, not a massive amount. Not futuristic technology, literally infinite energy. That means the speed of light is not simply difficult to reach. It is a built-in boundary woven into space-time itself. And this changes the entire way we should think about the cosmos. The universe is not stopping us through force or hostility. It is enforcing deep geometric laws that govern energy, motion, and reality itself. Relativistic travel does not fail because humanity lacks ambition. It fails because the structure of the universe transforms motion into destruction long before light speed is ever reached. The deeper you examine relativistic travel, the more unsettling the picture becomes, because every layer of physics seems to reinforce the same conclusion from a different direction. Space is not merely difficult to cross at extreme speed. The universe itself appears structured in a way that punishes anything attempting to approach the ultimate velocity limit. And what makes this so disturbing is that these are not speculative ideas or fringe theories. They emerge directly from the most tested equations humanity has ever produced. To understand how serious this becomes, we need to stop thinking about light speed as a science fiction destination and start treating it as a physical boundary with consequences that grow violently long before the limit is reached. Imagine a spacecraft attempting to travel to Mars at a significant fraction of light speed. At first glance, the idea seems incredibly attractive. Mars sits relatively close on cosmic scales. In theory, increasing speed should simply reduce travel time. Accelerate enough and the journey shrinks from months to days, perhaps even hours. But this intuitive picture ignores the fact that velocity fundamentally changes how matter interacts with the universe itself. At low speed, interplanetary space feels almost harmless. The environment appears quiet, cold, and mostly empty. Tiny particles drift through the solar system, but they are sparse enough that spacecraft can move through them safely. Radiation exists, but shielding and distance make it manageable. Humanity's current missions operate comfortably inside this low-velocity regime. Relativity changes everything the moment speed rises dramatically. As velocity climbs, even the smallest particles suspended in space become dangerous projectiles. A microscopic grain of dust moving relative to a spacecraft at relativistic speed carries extraordinary kinetic energy. Something smaller than a grain of sand could strike with explosive force powerful enough to tear through metal and vaporize internal systems instantly. Again, the dust itself is not dangerous in isolation. Velocity creates the danger. This is one of the most important concepts in relativistic physics. Motion is not passive. At extreme speed, motion transforms environments into weapons. And the problem extends far beyond dust. The cosmic microwave background radiation discussed earlier fills every region of space continuously. At ordinary speed, it is harmless. But as blueshift compresses those ancient photons into higher energy states, the front of the spacecraft begins experiencing concentrated radiation bombardment, unlike anything humans encounter naturally on Earth. At moderate relativistic speeds, the crew would already face intense radiation exposure. Shielding might reduce some effects temporarily, but shielding itself introduces another problem. High-energy gamma rays interacting with shielding materials generate secondary particle cascades. In other words, the protective barrier can become a source of additional radiation as incoming particles smash into it. The spacecraft slowly transforms into its own radiation chamber. And then there is heat. People often imagine space as freezing cold, which is technically true under ordinary conditions. But heat in physics is not simply about environmental temperature, it is about energy transfer. At relativistic speed, enormous amounts of energy begin concentrating into the front-facing structure of the spacecraft. The result is similar to atmospheric compression experienced during re-entry, except magnified enormously. Radiation deposits energy into the hull continuously. Microscopic particle collisions release heat. Electromagnetic interactions intensify. Every meter traveled increases thermal stress on the ship's structure. Eventually, the front of the spacecraft would begin experiencing temperatures beyond the tolerance of known materials. And even if future engineering solved one problem, another immediately appears underneath it. This is where quantum physics enters the picture in a way that feels almost surreal. The Unruh effect reveals something deeply counterintuitive about acceleration itself. According to quantum field theory, acceleration changes how observers experience the vacuum of space. The faster the acceleration, the warmer the vacuum appears. This means the spacecraft is not merely colliding with external radiation. Its own acceleration changes the physical behavior of empty space around it. At low acceleration, the effect is negligible. But to accelerate a massive spacecraft toward relativistic velocity within practical timeframes would require extreme force sustained over long periods. Under those conditions, the quantum vacuum begins behaving like a thermal environment. Space itself appears to heat up. This is not metaphorical language. It is a direct prediction of quantum field mathematics. To the accelerating spacecraft, particles emerge from what stationary observers would call empty vacuum. The faster the acceleration climbs, the more intense this thermal bath becomes. So, now the ship faces multiple simultaneous threats. Gamma radiation ahead, particle impacts from interstellar matter, thermal stress from electromagnetic compression, and quantum radiation generated by acceleration itself. All of this happens before reaching light speed. And then relativity introduces the final impossible obstacle: infinite energy requirements. Special relativity tells us that as an object with mass accelerates, its relativistic momentum increases dramatically. Each additional increase in speed requires more energy than the last. Near light speed, the required energy rises toward infinity. This is not an engineering inconvenience. It is a mathematical wall. No matter how advanced a civilization becomes, finite energy cannot push massive matter across an infinite requirement. The equations simply do not allow it. This completely changes the popular science fiction fantasy of effortless interstellar travel. The universe is not an open highway where enough technological progress eventually removes all obstacles. Instead, the structure of spacetime itself actively resists relativistic motion through unavoidable physical consequences. And perhaps the most profound part of this realization is that the universe never announces these restrictions emotionally. There are no cosmic warning signs, no visible barriers floating in space. The laws simply exist quietly inside mathematics, waiting for anyone bold enough to test them. The closer you move toward light speed, the more reality itself transforms against you. Radiation intensifies, matter becomes explosive, empty space begins radiating heat, energy requirements diverge toward infinity. Every layer of physics joins the same conclusion from a different direction, creating a perfectly unified system of limits. Once you accept that space-time itself may resist relativistic travel, the entire conversation about humanity's future in the cosmos changes. The problem is no longer technological in the ordinary sense. It is no longer about stronger engines, better fuel, or more advanced spacecraft materials. The deeper issue is that the laws of physics appear to contain built-in consequences that become increasingly destructive as velocity rises. And those consequences are not isolated problems. They reinforce each other with extraordinary consistency. This is what makes the situation so unsettling from a scientific perspective. Relativity, electromagnetism, thermodynamics, and quantum field theory all point toward the same conclusion independently. When entirely different branches of physics converge this strongly, it usually means we are encountering something fundamental about reality itself. To understand the scale of the challenge, consider what happens to time and energy as relativistic motion increases. According to Einstein's special relativity, time itself behaves differently for objects moving at extreme velocity. From the perspective of observers on Earth, clocks aboard a relativistic spacecraft begin running slower. This effect, known as time dilation, has been experimentally confirmed many times using atomic clocks and high-energy particles. At moderate speeds, the effect is tiny, but near light speed, it becomes dramatic. A crew traveling at relativistic velocity could experience only months passing on board while years or decades pass on Earth. From inside the spacecraft, the journey appears shortened not only spatially but temporally. This idea has inspired generations of science fiction because it seems to offer a loophole around the enormous scale of the universe. But time dilation is often misunderstood as a solution when it is really a consequence of the same physics creating the danger. The closer the spacecraft approaches light speed, the stronger time dilation becomes because the energy required for further acceleration rises explosively. Time slows, precisely because the ship is entering an increasingly extreme relativistic state. The same conditions producing temporal effects are also intensifying radiation exposure, thermal stress, and momentum barriers. In other words, the apparent benefit of relativistic travel emerges from the same physics threatening to destroy the vehicle. This creates a cruel symmetry in spacetime. The universe permits certain strange relativistic effects, but only by forcing travelers into conditions that become increasingly hostile to matter itself. And the hostility does not remain external. Eventually, it begins affecting the structure of the spacecraft on the atomic level. High-energy gamma radiation generated through blueshift does more than heat surfaces. It penetrates deeply into atoms, damaging crystal structures inside metals and disrupting chemical bonds throughout materials. Over time, prolonged radiation exposure weakens the integrity of matter itself. Electronics fail first, but eventually structural systems begin degrading as well. At sufficiently high energies, incoming radiation can even trigger nuclear interactions inside shielding materials. The hull stops behaving like passive protection and starts becoming an active site of particle collisions and secondary radiation generation. The spacecraft effectively enters a continuous microscopic bombardment event. Meanwhile, the quantum vacuum continues responding to acceleration through the Unruh effect. This is where the philosophical implications become almost impossible to ignore. Empty space, once imagined as nothingness, reveals itself as an active participant in relativistic motion. Acceleration changes reality itself. To a stationary observer, the vacuum appears cold and empty. To an accelerating observer, it appears warm and filled with particles. This means different observers moving differently through spacetime do not even agree on the basic state of emptiness. That realization is extraordinary because it suggests that concepts we treat as objective, like temperature and particle presence, can depend on motion itself. And as acceleration intensifies, so does the apparent temperature of the vacuum. For ordinary vehicles, the effect remains undetectable. But near the extreme accelerations required for practical relativistic travel, the mathematics predicts rising thermal radiation strong enough to become physically destructive. The spacecraft would not merely be heated by external radiation anymore. It would be immersed in heat emerging directly from its own accelerated interaction with quantum fields. This changes the entire emotional image of relativistic travel. Science fiction often presents high-speed spaceflight as smooth and elegant, with silent stars drifting past polished windows. Real physics paints something far harsher. The spacecraft would exist inside a violent storm of radiation, thermal stress, particle collisions, and quantum effects, all generated by motion itself. Velocity becomes environmental transformation. And beyond every one of these obstacles stands the absolute barrier imposed by energy requirements. Relativity does not merely say that reaching light speed is difficult. It says that for objects with mass, the exact speed of light is unreachable under finite energy conditions. As velocity increases, relativistic momentum rises without limit. Every additional increase in speed demands disproportionately more energy than the last. Near light speed, the curve becomes effectively vertical. Infinite energy would be required to actually cross the boundary. This is not a technological failure, it is geometry. The structure of spacetime itself defines light speed as a limit embedded into reality. Massless particles like photons move at that speed naturally because they do not require acceleration into it. Massive objects do, and the universe refuses to provide a finite path across that divide. This forces a difficult but important realization. Humanity's dream of simply building faster and faster ships until interstellar travel becomes easy may fundamentally misunderstand the nature of reality. The universe is not a passive stage waiting for engineering to conquer it. It is an active system governed by precise mathematical rules that impose consequences long before ultimate limits are reached. The closer we move toward light speed, the more the universe changes around us. Ancient background radiation transforms into lethal energy. Empty space begins radiating heat. Matter experiences atomic damage. Time itself distorts. And energy requirements diverge toward infinity. Every layer of reality participates in enforcing the boundary. And this leads directly into the next stage of the story, where the question becomes even more profound. If relativistic motion is fundamentally destructive to matter, then perhaps the future of interstellar civilization will not depend on outrunning the universe, but on finding entirely different ways to move through it. Once the idea of simply accelerating toward the stars begins collapsing under the weight of real physics, humanity is forced into a far more uncomfortable realization. The dream of relativistic travel may not fail because civilization lacks intelligence or technological maturity. It may fail because the universe itself is structured in a way that makes brute force motion fundamentally incompatible with survival. And that changes the direction of the entire conversation. For over a century, science fiction has imagined progress as a straight line. Better engines lead to faster ships. Faster ships lead to interstellar civilizations. Eventually, humanity spreads naturally across the galaxy through sheer technological advancement. But relativity suggests that speed itself may become the enemy long before distances become manageable. This creates an extraordinary paradox. Space is unimaginably vast, yet the universe imposes strict limits on how quickly anything with mass can cross it. At first, this sounds deeply pessimistic. But in reality, it reveals something far more interesting about the nature of advanced civilization. If direct relativistic acceleration becomes increasingly destructive, then truly advanced species would likely stop trying to overpower physics and instead begin working with the deeper geometry of space-time itself. In other words, the future of cosmic travel may depend less on propulsion and more on manipulation of space and time. This is why concepts like warp drives and wormholes continue attracting scientific attention despite sounding almost mythical to the public. Unlike traditional rockets, these ideas do not attempt to accelerate matter through space-time toward light speed. Instead, they attempt to alter space-time itself. That distinction is critical. A conventional spacecraft moves through space. A warp-based concept attempts to move space around the spacecraft. The most famous example is the Alcubierre warp drive proposal introduced in the 1990s. According to the mathematics, space-time in front of a vessel could theoretically contract while space-time behind it expands. The spacecraft itself would remain inside a local bubble where it is technically stationary relative to nearby space, avoiding many of the relativistic problems associated with direct acceleration. In theory, the bubble itself moves rather than the ship. This idea became famous because it appears to bypass the light speed barrier without technically violating relativity. The spacecraft never locally exceeds light speed inside its bubble. Instead, space-time carries it along. But once again, physics responds with brutal complexity.